Hello, I am Takanori Saito of Anritsu Corporation's Sensing and Devices Company. Today, I'm going to introduce our wavelength swept light source for implementing non-contact, high-resolution distance and shape measurement. Here are the presentation contents. First, I'll talk about development of Ofdr systems, followed by distance measurement using Ofdr and Ofdr features. Then I'll move on to shape measurement systems, examples of shape measurement, and finish with conclusions. First, I would like to explain the development of Ofdr systems. Current industrial measurement systems require non-contact shape measurement with micrometer or order accuracy for products ranging in size from centimeters to meters. Measurement methods using light are being adopted to satisfy this need for non-contact measurement. As shown here, light sources are divided into different types for distance and shape measurement. First, there are swept light sources that sweep either wavelength or optical frequency using a method called optical frequency domain reflectometry, or OFDR, which is the term we will be using here. Frequency modulated continuous wave, or FMCW, is another name for this technology, but both are exactly the same. The measurement range of OFDR is about several meters. This measurement range is not the work distance, but means that a range of several meters can be measured freely. Moreover, the accuracy of this measurement is several micrometer. The method using a pulse light source is called the time of flight or TOF method. It measures the time until the light pulse reflected by the DUT is received. This is the LiDAR technology currently used by self-driving vehicles. This method has a range of several hundred meters, but a lower measurement accuracy of about 10 centimeters. The optical comb method also uses a pulsed light source, but achieves an accuracy of about 1 micrometer. However, the measurement range is limited to just 6 millimeters. The method using a continuous white light source is used for white light interferometry. This white light source can measure a wavelength level range of around 1 micrometer, but with an extremely high accuracy of 1 nanometer. Looking at these methods, we can see that the Ofdr method using a swept light source is best for industrial shape measurement. Consequently, Anritsu has started development of shape measurement systems based on the Ofdr method using swept light sources. Continuing on, this slide explains the principle of distance measurement using Ofdr. The Ofdr system is composed of a swept light source, interferometer, and optical receiver. The frequency of the light output from the swept light source increases linearly with time. The light from the swept light source is split first into two paths by a coupler. The first path is indicated by this blue line, and is called the reference path. It passes to an optical receiver via a second coupler. The other path indicated by the red line is called the measurement path. After passing through the first optical coupler, it reaches the lens via circulator from where it is transmitted through free space to illuminate the DUT. The light reflected back from the DUT passes back through the lens, where it is coupled to an optical fiber and passes via the circulator through the second coupler to reach the optical receiver. The optical frequency of the light following the blue and red paths is the same until reaching the first optical coupler, but since the reference path LR and the measurement path LM are clearly of different lengths and LM is much longer, the frequency of the light passing through the blue reference path when received by the optical receiver is different from the frequency of the light passing via the red measurement path, which has a slightly lower optical frequency as shown by this graph. This frequency difference corresponds to the distance. The optical receiver outputs a beat signal at the same frequency as the difference between these optical frequencies. When this beat signal from the optical receiver is sampled by an analog digital AD converter and fast Fourier transformed FFT, plotting the distance difference between LM and LR on the horizontal axis, and the FFT spectrum power P on the vertical axis detects the peak position for the LM and LR paths. This detected peak position is used for distance measurement and is the principle of Ofdr measurement systems. The previous explanation explained a Mach-Zehnder type interferometer, but it is not necessary to be limited to this type of design, and there is also a Michelson interferometer. However, since a balanced receiver cannot be used as the optical receiver by the Michelson type interferometer, it cannot cut AM noise, unlike the Mach-Zehnder design using a balanced receiver, which is now used more generally in this field. Moreover, there is another Mach-Zehnder configuration that is simpler because it does not use a circulator. This next slide explains distance measurement resolution using OFDR. According to this equation, distance resolution, dz, is inversely proportional to the swept optical frequency or wavelength width. This explains an actual numeric value when measuring with a center wavelength of 1550 nanometer and a sweep width of 20 nanometer. 20 nanometer is equivalent to an optical frequency of 2.5 terahertz, and in this case the resolution is 60 micrometer. In other words, when plotting distance on the horizontal axis and FFT power on the vertical axis, the peak is detected with a width of 60 micrometer. However, the peak position itself can be determined on the order of micrometer by peak detection. Consequently, based on this, the distance measurement resolution, or in other words measurement accuracy, using OFDR is micrometer order. Next, I would like to explain the maximum measurement range using OFDR. This shows an example when the difference in the distance between the reference and measurement light paths is small. In this case, when FFT is applied, a peak is detected at the low frequency side, or in other words at the closer distance side. The beat frequency is also low. When the DUT is further away, since the difference in the lengths between the reference and measurement paths is longer, the beat signal frequency also becomes higher and the peak is detected further away. The furthest distance that can be detected is limited by the AD converter band because the signal cannot be detected beyond this point. The coherence length of the light source is another limiting factor. As the difference in the distances between the reference and measurement light paths becomes larger, the correlation disappears completely. Under these conditions, when the beat signal is detected and FFT is applied, the peak expands to the width of the original laser width, generally becoming millimeters wide. Under this type of condition, the measurement accuracy becomes extremely poor even if a peak can be detected. Therefore, assuring long distance, or in other words, a wide measurement range, requires both a wideband optical receiver and AD converter, as well as a light source with a long coherence length. In simple terms, long-range measurement using OFDR systems requires a high-coherence light source, which has resulted in Anritsu's development of this light source. This is the high-coherence wavelength swept light source that we have developed, and is released on July 1, 2021. It has a center wavelength of 1550 nanometer, and a maximum sweep width of 110 nanometer. There are two models with different sweep frequencies of 1250 Hz and 150 Hz. The sweep waveform is sinusoidally repeatedly from the short to long and long to short wavelength. The maximum output is better than 10 dBm, and the coherence length of the high-speed 1250 Hz model is longer than 10 meter. The slower speed 150 Hz version has a coherence length of longer than 100 meter. Okay, this slide summarizes the various processes used to calculate distance by OFDR. The procedure is a continuous sequence for each sweep composed of sampling, linearizing, delay compensation, measurement of difference in optical path length of reference interferometer, FFT, peak search and distance conversion. The next few slides explain each of these processes. First, I'll explain linearizing. This is the key processing for OFDR. Although explained as sweep nonlinearity, in the explanation of principles, it was explained that sweep light source optical frequency changes linearly against to the time. If a beat signal can be obtained under this condition, a sharp peak can be calculated when the frequency is constant like this and FFT is applied. However, actual swept light sources do not produce such a clear beautiful line, and at first sweeping may be impossible or may actually produce this type of nonlinear line. For example, using the Anritsu wavelength swept light source, the sweep shape is sinusoidal and changes repeatedly from slow to fast to slow. As a result, the obtained beat signal also changes according to this frequency sweep speed. When FFT is applied to this type of obtained beat signal, an abnormally broad peak is calculated from which an accurate peak cannot be detected, causing extremely poor measurement range accuracy. So that's linearization, and here is an example of an actual optical system, which is in fact a conventional OFDR optical system to which a reference interferometer has been added here. In this case, the optical system has a Michelson interferometer attached. Due to this delay length LAUX, a beat signal that always depends on LAUX's output as the reference signal. Linearization uses this reference interferometer signal to assure the sweep speed. At actual use, an 8-meter optical fiber equivalent to LAUX is attached as the free spectrum range, which is 12.5 MHz in this case. In other words, each time the light source swept frequency sweeps 12.5 MHz, the output beat signal increases peak by peak. In addition, use of a Michelson interferometer here, with a Faraday mirrors improves usability by assuring that the polarization wave output from here is in exactly the same state as the input to the coupler. In other words, the state of the polarization coming back from the top branch and the state of the polarization coming back from the bottom branch are exactly the same at return to the coupler, meaning the interference output is always stable. This optical system combining the Michelson interferometer and Faraday mirrors is extremely useful. There are actually two types of linearization processing: hardware linearization and software linearization. Each method has its merits. Hardware linearization uses an AD converter, featuring high-speed processing and a wide bandwidth up to the limit of the AD converter bandwidth. The disadvantages are the difficulty of compensating for delay and dispersion due to use of a physical mechanism. Conversely, with software linearization, computation is performed by either a PC, CPU, or GPU, or by a device such as an FPGA. Although this has the merit of easy compensation for delay and dispersion, the disadvantage is the complex programming of these processes. Right now, I'll explain hardware linearization in more detail. In this slide, the red curve is the reference interferometer signal, and the yellow curve is the measurement interferometer signal. The signal shown in red is input to the AD converter clock, and the signal shown in yellow is input to the normal measured signal channel. By doing so, the AD performs sampling at each rising edge of the reference interferometer signal. The measurement interferometer signal is AD sampled at each time the reference interferometer free spectral range, FSR, is swept by the optical frequency. This FSR is 12.5 MHz as mentioned previously. FFT processing of the sampled data produces a sharp reflection peak, because sampling is performed at a constant optical frequency interval. This is the sampling method using hardware linearization. Continuing on, this slide explains software linearization. This method performs simultaneous measurement of the reference interferometer and measurement interferometer signals at the AD converter. When the reference interferometer is X here, the phase of X is calculated for a 90 degrees phase drift after applying Hilbert transformation with a digital filter. Consequently, the phase of both the 90 degrees phase drifted Y and the original X waveforms can be calculated to find the phase of the reference interferometer signal. In this case, the change is from -pi to pi and then returns to -pi. The continuous phase is calculated by adding 2π to the phase at the return point in a process called unwrap. Equal division processing is performed after continuous phase calculation. The measurement signal at the equal divisions is extracted and plotted as the green dots here. When these are aligned and FFT is applied, the optical frequency becomes the data measured at equal intervals. This is the sampling method using software linearization. Here is the data extraction method. It is quite simple with red dots representing the measurement points which are aligned at equal time intervals. Extracting data for an intermediate point between two measurement points requires a simple interpolation calculation. Now let's look at delay compensation. As explained previously, an 8-meter fiber is connected to the reference interferometer. Connecting the fiber creates a difference between the frequency of the light received by the optical receiver of the reference interferometer and the frequency of the light received by the balanced receiver of the measurement interferometer. If this difference is large, linearization cannot be performed with good accuracy. Consequently, this 8-meter fiber with the same delay is inserted just before the measurement interferometer to compensate for the drift by ensuring that the frequencies of the light received at the two detectors is matched, and supports high-accuracy linearization. Incidentally, only hardware linearization requires insertion of this fiber. Software linearization can compensate for the delay by calculation. Now let's look at reference interferometer (FSR) measurement. This red curve is the measurement interferometer interference signal. The signal that becomes the reference wavelength represented as the blue curve is sampled simultaneously. In this example, the signal of the etalon in the Anritsu light source is used as the reference wavelength. The etalon peak wavelength has been measured with high precision beforehand. Using this value, the etalon peaks, or in other words the sample positions, are plotted first on the horizontal axis, and the optical frequencies calculated from these peaks are plotted on the vertical axis. Since etalon peaks are detected at 5 points, the peaks for 5 points are plotted like this, and the FSR of the reference interferometer is found as the gradient of the curve by the least squares method. Knowing this FSR makes it possible to calculate the reference interferometer delay length of 11,870.810 mm with very high precision. Finally, let's look at the distance conversion method. In this example, 131,072 samples were captured and subjected to Fourier transformation. As a result of doing so, the distance to the halfway 65,536th point is the halfway distance of the delay length found previously. In other words, in this case, 5,935.405 mm. By knowing the length of this position, the distance can be found by proportional calculation. This slide summarizes the Ofdr sequence of processes. At hardware linearization, the reference interferometer signal is input to the AD clock, and then the measurement interferometer and etalon signals are sampled simultaneously. Next, the reference interferometer optical path difference is calculated and peak search is performed after applying FFT before calculating the distance. On the other hand, with software linearization, the reference interferometer, measurement interferometer, and etalon signals are sampled simultaneously, followed by calculation of the reference interferometer signal phase and conversion to the continuous phase before extracting the measurement interferometer signal corresponding to the equal divisions points. Subsequently, in both cases, the reference interferometer optical path length difference is calculated, FFT is applied, and the reflection peak position is detected for conversion to distance. To continue, what is the actual measurement resolution? Here are the measurement results obtained for 1.6 terahertz equivalent to a wavelength of 13 nanometer sampling and applying FFT. This peak is magnified here. At 1.6 terahertz, although this peak has a width of 90 micrometer, theoretically, 100 micrometer can be actually measured. This was followed by sampling 260,000 points and thinning each measured data by 1. By doing so, although the number of sampling is the same 130,000, the data can be sampled across a wavelength sweep range of 3.2 terahertz. The calculated resolution in this case is 45 micrometer, and the actually measured peak width is 50 micrometer, clarifying that the obtained FFT spectrum is about as calculated. Okay, in this slide, we measured the precision of this distance measurement system using Ofdr by measuring the distance between the collimator lens of the optical system and a black alumite target on an optical rail. These are the results for 10 seconds of real measurement. The distance between the two was about 540 mm, a standard error of 0.2 micrometer. Consequently, it is clear that the measurement accuracy is 0.2 micrometer. Achieving this level of precision continuously is not so easy. In this case, the height of the peak reflected from this DUT is small, so the accuracy is obviously poor. This measurement is plotted on this graph where the horizontal axis is the signal height with a scale of 80 to 160. The noise level is about 80 dB, so the SNR is 1 here. The measurement accuracy is about 2.5 to 3 micrometer at the peak, where the SNR of this line is 10 dB and is almost micrometer order. Therefore, we can clearly measure distance with micrometer order accuracy if the signal-to-noise ratio, SNR, is at least 10 dB by applying FFT. As shown at the right of this graph, the measurement accuracy improves as the signal becomes stronger. At a signal strength of about 130 dB, we can see that the distance is measured with an accuracy of about 0.2 micrometer. However, when the signal strength becomes too high, the optical receiver is saturated, causing saturation of the AD converter and degrading the signal quality, which in turn causes poor measurement stability and worse measurement accuracy. Looking at this, we can say that the dynamic range of the signal is about 60 dB to achieve a measurement range with micrometer order accuracy. Incidentally, here, we define the reflectivity equivalent to the weakest optical signal power of 90 dB. In other words, it is the proportion of light returned to the fiber by the collimator lens versus the light emitted from the collimator lens. From calculation, we can say that measurement with micrometer order accuracy is possible if light is returned with a reflectivity of about the -8th power of 10 or 0.01 ppm. Let's look at how much the reflection effect changes with actual materials. First, the picture on the left is the optical material black alumite, followed by polished stainless steel, and then by optical glass with an extremely precise surface accuracy. We estimated the degree of accuracy when measuring the distance to these materials. First, each of these optical materials was placed on a turntable that was rotated to measure the change in power and reflectivity with incident angle. The incident angle is plotted on the x-axis with signal strength on the vertical axis, and the area where distance can be measured with micrometer order accuracy is in the range from 90 to 150 dB. Looking at the curve for black alumite, the reflectance is not so strong, and does not decrease very much even when light strikes the material perpendicular to the surface, and the plotted line does not fall greatly with increasing incident angle, making measurement possible up to an angle of 88 degrees. Extremely black alumite can be measured easily, although we might have expected that a material with such low reflectivity would be difficult to measure. It can be measured easily. Looking at polished stainless steel, which is very reflective when light strikes the material perpendicular to the surface, the accuracy becomes worse as the signal becomes too strong. It is clear that the incident angle limit is about 70 degrees where the signal strength becomes too weak. The plotted line for optical glass falls steeply, and it is clear that the limit is around 30 degrees. These diagrams summarize the above results. Black alumite can be measured even when barely visible at 88 degrees, polished stainless can be measured at an incident angle of 70 degrees, while optical glass can be measured at 30 degrees. This slide shows the external view and block diagram of this shape measurement system using Ofdr technology. The top half of the photograph is a notebook PC workstation, and the bottom half is the wavelength swept light source with built-in interference optical receiver, AD converter, and automatic stage controller. This is the collimator lens with an aperture of 20 mm connected to an optical fiber. It has two automatic stages for tilting and turning to measure shape. Moving on, the next slide shows some actual measurement results. This is a model steam train with a low reflectance black surface and stainless steel driving wheels. It was measured from a distance of about 60 centimeters. This is the steam train measurement result. It is color separated according to distance. The distance range between the blue and red colors is about 20 mm, and it is clear that fine detail can be measured faithfully. Next, this is the measurement result for a Japanese 100 yen coin measured from a distance of about 1 meter. The graph on the right side shows the cross-section of the measured surface. From this we can see that the coin has a diameter of 22 mm and a thickness of 1.5 mm. In addition, the projection of the coin surface relief indicates the 1, 0, and 0 numbers on the coin face have heights of about 150 micrometer. To continue, this image shows a slightly wider measurement range. It is the concrete walls at a corner of our research laboratory with the top edge of an LCD monitor in the foreground and a bench with solder workstation, cables, tools, electrical cables, etc., in the background. The depth from front to back is 2 to 3 meters. This shows the measurement results color separated over a range of 2 to 3 meters. Even slight depressions in the concrete wall at the back are visible. Additionally, the cable ties on the two thicker cables can be seen too. It is clearly possible to measure the distance from the face of the LCD monitor in the foreground to the cable of the solder workstation in the background. Using OFDR, it is possible to measure the distance to multiple reflection points. For example, as shown here, pairs of collimator lenses and DUTs can be connected in a cascade using delay fibers. The graph on the right shows the FFT results obtained from this setup, indicating that each reflection peak can be measured simultaneously using the lengths to L0, L1, and L2. By measuring multiple points, it is also possible to measure the thickness of an opaque body. In this setup, the optical signal is first split with one signal passing to a collimator lens on the right side of the DUT via a fiber delay, while the other passes to a lens on the left side. The collimator lens on the right side measures the distance, L-right, to the right face of the DUT. And, the collimator lens on the left side measures the distance L-left to the right face of the DUT. Since the distance L between the two collimator lenses is known, the thickness of the DUT can be calculated using this equation. Here are the measurement results using this method. The top graph shows the FFT results with no DUT between the collimator lenses and measures the distance from the left collimator lens to the right collimator lens. The opposite direction from the right to left lens is the same. Under this condition, we can see 4 peaks showing the distances between the two lenses. The graph at the bottom with the DUT in position shows the measurement results from the left collimator lens to the left face of the DUT, and from the right collimator lens to the right face of the DUT. Consequently, the thickness of the DUT can be calculated as shown above. This slide shows an example of using this system to measure the fins of a heatsink where the fins are clearly visible. We also measured an optical bench, A with a black alumite base to measure the counterbore holes. This diagram shows the block is 1 cm with counterbore holes at the left and right sides. This depth is exactly in the middle of the plate. Another optical bench B with drilled holes was also measured. The base of the hole has a clear, sharp shape. This peculiar signal is an error signal because the measurement was not good. Despite the error signal, we can still measure the depth direction and the thickness accurately. This next slide shows an example of measuring the change in distance between two buildings, using the low-speed wavelength swept light source with a long coherence length. This OFDR system is placed in the building N on the left, and the optical signal is returned by reflection from the wall of the building S on the right to measure the distance between the two buildings. During a 40-minute measurement period in the evening, we can see that the distance is clearly increasing by about 200 micrometer. We think that this is probably due to the tilt of the buildings changing as the temperature dropped during the evening. The measurement precision at this time was about 23 micrometer with a standard error of 23 micrometer. By using this method, we think it would be possible to measure small changes, such as deformation and aging deterioration, in architectural structures. This OFDR technology is exactly the same as SSOCT. Put simply, although distance measurement only detects peak positions, OCT can measure the distribution of the reflections using the FFT spectrum. This shows a measurement example looking at the cross-section by scanning in the horizontal direction. Although this is the principle of OCT, there are clear differences in resolution here. When measuring at a sweep width of 1.6 terahertz, the resolution is about 90 micrometer. This is the cross-section appearance of a sponge under these conditions. When the sweep width is expanded to 3.2 terahertz, the resolution becomes 45 micrometer, or twice that of the above calculation, and the cell walls of the sponge become clearer. OFDR can be used for this type of cross-section measurement. So, to summarize the above, We have configured a shape measurement system using Ofdr with a high coherence wavelength swept light source. As well as having a wide measurement range and wide reflectivity dynamic range, it also supports high accuracy micrometer order measurement. Even difficult to measure, low reflectance materials, such as glass and stainless steel, can be measured. This system can measure distances up to 6 meters with an accuracy of 0.2 micrometer at a measurement speed of 1,250 points per second. Reflectance rates including lens coupling up to 0.01 ppm can be measured. We think these specifications are sufficient to meet industrial measurement requirements. This concludes my presentation. Thank you for your interest and attention.